Thanks so much, Martin. And yeah, thanks for hanging out. Excited to dive into some of the work that we are doing to improve ICM going forward, and also super impressed with the flow of all of these presentations from Andrea and Nelia. We'll hopefully be building off of those and expanding upon some of those topics. Yeah, so I'm going to touch briefly upon where we've been, where we currently are as far as ICM usage and our focuses of as a team, and then where we're going also. And fortunately, I think we all have a pretty good overview of ICM already from Andrea's talk, and still wanted to share this beauty of a diagram that has been around for like 3 years now, and wanted to keep the streak going for how many times it's been up in a presentation. But I do think it's also a good foundation of how ICM works, succinct, all on one page. So you have one L1 now. This image predates the L1 terminology, so forgive me on that. That wants to send a message to L1B, and the first step is that a transaction is sent on this L1 that calls the ICM precompile, notifying all of the validators that then process that transaction that a message has occurred. And what that does is it makes the validators willing to sign that message using their BLS key. Then the relayer is then this bar. When it hears of this message being finalized, it queries the validators of L1A for their BLS signatures, packs it in a transaction, sends it on subnet B, and during the verification of that message, subnet B actually looks up the validator set of L1A from the P chain in order to do the BLS key aggregation and signature verification. So this has all been touched upon, but wanted to kind of set that as the foundation for everything we're doing going forward. I mentioned this during the panel, but since we were last together in Buenos Aires, we've seen huge growth in the number of chains actually using ICM on mainnet, which has been super, super exciting for our team to see. Very reassuring that we're building something that is useful and that we're finally starting to see a good number of projects launch really cool, really useful applications using this interchain messaging primitive. The fun fact, March 2024, which was when ICM launched, those messages were sent by our team to test it out on mainnet. So there was like literally 2 messages there, so it's just one chain. And it wasn't until September, October, where we started to see many projects get onto mainnet using ICM, including many of these awesome teams who are here today. So if you're listening, thank you. One for using our tech. It's gives us a lot of pride that you chose ICM to build on, and there's a lot of really cool projects and use cases on this list. Tesseract, which I mentioned before, and I think it's going to be presented later, is building a cross-chain swaps using ICTT. Satly is using BTC as their native token, enabled by ICTT as well. We have Dex a lot, using ICM for their cross-chain deposits, I believe, and order placement for their decentralized CLOB. And the Kuroshi team also, where is it? Here it is, just started using ICM recently on mainnet, and they're actually using Avax as their native token, which is a very cool use case. So the usage of their L1 is actually burning Avax, which I think many people here would be happy to learn. Yeah, so it's been really exciting to see all of these integrations come about. It's also been really great in order to get feedback on ICM from all of these teams. So thank you for all of that, and please keep it coming. It's how we are constantly trying to improve ICM, not just at the protocol level, but making it as easy as possible to integrate with. So that's where we are. And now we'd like to talk about the work that we have planned for the next 6 to 9 months or so, really through the end of this year. And breaking that down, it falls into really 3 primary projects. One is an ICM external signer integration, 2 is the P-chain view epoching, and 3 is ICM to external ecosystems, which I believe there was just a question about earlier, so excited to get to that one. Starting off with the ICM external signer, though. So currently, back on the diagram of how ICM works from end to end. I mentioned there's a step where the relayer finds out that the message was sent on the origin chain, and it needs to query validators of that chain for their BLS signatures, and it performs that BLS aggregation then. The way that request typically works is that it uses Avalanche Go's P2P networking library in order to send app requests to the validators of the source chain. And when those nodes receive that request, it checks if the message to be signed has actually been finalized on the chain that they're listening to. And if that's the case, then it's willing to sign that message using its BLS private key. Those BLS private keys are currently kept on disk for Avalanche Go. When you start Avalanche Go for the first time, if it doesn't exist, it will randomly generate one. And then on all subsequent startups, it will use the same key. So that key is also read into memory, which for networks with many thousands, many hundreds at least of validators, that's pretty good. Right? You can't easily access sufficient validator stake weight in order to forge a message. You'd need to be able to access somehow 67% of the stake weight of a given L1 or the primary network. And if there's so many nodes with a decent stake distribution, that'd be very hard to do because it's spread across so many different teams, so many different deployments. So that's okay. But if we have a much smaller L1, but say only 5 validator nodes or 10 validator nodes, and all of those nodes are co-located or in just a small number of AWS accounts, that's not so great, right? Then you have really a 3 or 4, or 4 or 5 rather, multi-sig bridge, just like any other traditional bridge. And that's not what we were hoping for when we built ICM. Obviously, when the best way to solve for this problem is to get back to more of this case, where you have a more decentralized validator set. However, that's not always practical or easy to do right off the bat. So with the ICM external signer, what we're hoping to do is increase the practical security of the usage of ICM for chains with small validator sets. And the way that it works is that the BLS key, which was previously kept on disk and read into memory of the Avalanche Go node, is now moved external to the node into a hardware security module, HSM. And the key is generated in that HSM and actually never leaves the HSM itself. When there is a signature request, say from the relayer to the Avalanche Go node, the Avalanche Go node checks if it is willing to sign that message, and if so, since it doesn't have the key itself, it requests a signature from this hardware security module that can generate the signature and return it. And the integration here is with Cubist's signer product, and they have a number of great projects that are already live for Ethereum staking keys, keeping those secure in HSMs, as well as the core seedless wallet integration that is powered by Cubist. So we're super excited to leverage their technology for this use case and have any Avalanche Go node operator be able to plug into that to help secure their deployments. Another really cool extension then of their signer product is that you don't just have the key in an HSM able to be rotated, say if you had a compromise of the node itself, but you can write custom policy engines on the HSM side that are enforced for determining whether or not a message should be signed. Since ICM messages generally have a well-specified format, and given applications have well-specified payloads inside of those messages, the logic on the signer side can define custom rules, say if this message is bridging over $1 million, then wait for an hour, or require manual sign-off by some number of YubiKeys before the HSM is actually willing to provide the signature for even more practical security. Because the real risk here, as I believe Gautier from the Suzaku team mentioned yesterday, is that funds from, say, the C chain, any token that exists there, are bridged into L1s, and then they are controlled. Those funds are controlled by the validator set, which is the same type of trust assumption as using that chain itself. However, if the chain gets compromised, those attackers could theoretically steal the funds on the C chain then themselves, not just on the network, and that creates a larger security risk than just for the network itself, which could always be hard forked in the future if necessary. So the ICM external signer integration with Qubist enhances the practical security of ICM usage for L1s with relatively small validator sets. We really want to set out to make this protocol as secure as possible. We started off that mission by removing all trusted parties, which is a great first step, but that also relies on the chains themselves being secure, and we think this is a great further step in that direction to not necessarily increase the theoretical security of the chain. You know, if 75% of stake weight is actually malicious, they could still try to, it doesn't increase the theoretical security of the chain, put it that way, but it does increase the practical security by moving those keys off into the HSMs. Great. The second project I wanted to touch on here is ACP 181, which is a new ACP for P-chain view epoching. So just going back to this diagram of how ICM works, a very important step when verifying an ICM message is that the receiving chain or the verifying chain needs to look up the validator set of the source chain in order to know how to verify the BLS aggregate signature. And so the way that it does that is that it queries the P-chain, which is just a read operation, so it doesn't actually put any load on the P-chain, for the validators of subnet B, of subnet A actually, at height X. And the reason why height X there is important is because if different validators have different views of the source chain's validator set, they will get different verification results of that message and potentially have non-deterministic execution of the transaction because some validators might think it's a valid ICM message and other ones might think it's not. And that's because, say, I am reading the validator set at height X, you're reading the validator set at height X plus 1. In that latest block, a new validator with a large weight was added. So now the signature that I'm verifying at height X maybe met that 67% threshold, but with the new validator added, if they didn't participate in the signature, then it did not meet that threshold, so you think the signature is invalid, while I think it's valid, now we have problems. So the real question here is how do we define what height X should be? And this is how it currently works, which is that all L1s use what's called the proposer VM, which wraps the inner VM, which in most cases today is the EVM. And the proposer VM, each proposer VM block has a pointer to a recent P-chain block. The builder of the block proposer, on the L1 gets to specify the P-chain block that they have seen as the latest block, more or less. So you can see here, say, block L1 on the L1 chain points to P-chain block 1. The block 2 also points to block 1 because there hasn't been any more blocks on the P-chain. But now when L1 block 3 comes about, that block proposer has seen block 2, since that happened before in time, and they then advance the P-chain pointer height to the latest block. So as we continue on, it's not super strict. You might see, for instance here, L4 doesn't point to P3, even though P3 is right around the same time, because that node just hasn't seen the block yet. So it's not necessarily deterministic what block will be set, or rather what the P-chain block height pointer will be set to. It's kind of a best effort approach. And the issue here is that the P-chain pointer can advance basically arbitrarily in the next L1 block to be produced. And it requires on-demand P-chain queries during L1 block's execution to actually verify the ICM messages in that block because of the fact that the P-chain block can change arbitrarily from one block to the next. So not knowing what the next P-chain height to be used is makes it difficult to validate, or rather makes it difficult to generate valid ICM signatures, because if I am a relayer and I'm constructing an aggregate signature from height P2, but by the time my transaction gets included in a block, we're pointing to block height P4. Now my signature that I generated from aggregating the validator signatures has become invalid. And so a naive way of trying to solve for these problems is that we'll just say for a certain period of time, we should always point to the same p-chain block. So all of these L1 through L4s point to p-chain block P1, even though there's been more blocks since then. But then once we cross this time threshold, we'll update it to the latest height then. Unfortunately, this still has the same problem in the transition of the epoch from the first time period to the second, because during that transition, you still don't know what the next block is going to point to as far as the p-chain height. And in order to validate the message and do this on-demand p-chain query during L1 block execution, that's an expensive lookup operation, which causes the verification of these ICM signatures to cost more gas. So this is the actual diagram of how ACP 181 works, and it's somewhat involved. I think I put this diagram together. I was like, oh, this is super nice. And then I came back to it the next day, and I was like, oh, I actually probably made this more complicated than it needed to be. But we'll break it down one step at a time. So each block on the L1 has two p-chain pointers. One is the p-chain epoch height, which is the height that's used for ICM verification. And then the second is the p-chain height, which is the current p-chain block. So you can see the yellow pointers here are the p-chain epoch height, and the blue pointers are the current p-chain height. Now we define the epochs, which is this period of time, as follows. An epoch n is defined to be one or more blocks. It's defined by the one or more blocks that it contains. And the first block in an epoch is the block that follows the last block in the final epoch. So this is kind of a recursive definition. We call the last block in epoch n-1 the ceiling block, and then define what it means to be a ceiling block here, which is that the block in epoch n, the last block in epoch n, is the first block with a timestamp at or past the timestamp of ceiling block SB plus the time period D. And that's the block that seals epoch n. So the example here would be L5 is actually the block that seals the first epoch, and that is because it is the first L1 block to be D seconds after L1. And then I think at the end here we can also see L9 seals this second epoch because it is after D seconds have passed since the timestamp of block L5, which was the block that sealed the previous epoch. The p-chain height of each block is set by the block builder. Similar to how it's done today, it can advance arbitrarily. It must be monotonically increasing within certain bounds. This is the same as it is today, except the p-chain height is actually no longer used for the ICM verification. We always use the p-chain epoch height so that it's consistent for that period of time D. And lastly, if a block's parent sealed an epoch, then its p-chain epoch height must be set to its parent p-chain height. So this is how we handled the transition case smoothly. When you see a block that seals an epoch, you know the p-chain height of the next epoch that will be used. The way that works in this diagram here, so we see block L5 seals the first epoch. Its current p-chain height was P5. So we're still using p-chain height P1 for the verification of block L5, but we also know that block L5 sealed epoch 1. And now for the next block, the p-chain epoch height pointer is the same as its parent's block current height. So when L5 is produced, we know that it is sealed the first epoch, the next block will be in the next epoch, and must have the p-chain epoch height set to the current block of L5. Otherwise, if your parent isn't a sealing block, then you keep the same p-chain epoch height, which is why all blocks in the epoch point to the same p-chain height. So why are we doing this? One, it makes ICM signature construction far more robust because you always know what p-chain height will be used in the verification on the L1 when you're sending the transaction. And two, it is far less expensive to actually validate the ICM signature. And that's because when you see a sealing block, when the verifying VM receives the sealing block, it can prefetch the validator sets at p-chain height P5 and already have them in memory by the time block L6 comes around, rather than needing to do an on-demand lookup of, okay, I'm validating this new block, it's using a new p-chain height, and now I need to go fetch the validator set from that height. We have prefetched the blocks into memory and don't need to worry about any expensive disk lookups. So that's ACP 181 in a nutshell. I'm running a bit short on time, but the final project on our roadmap is ICM to external ecosystems. And the goal of this project is to allow Avalanche L1s to connect out of the box with any other proof-of-stake blockchain. Avalanche ICM works today for all L1s because those L1s register their validator sets on the p-chain, so they all have a common view of each other's validator sets, which allows for this type of verification. That's not the case for external ecosystems. As great as it would be if Ethereum decided to post their validator sets onto the p-chain and enable this that way, we're not waiting on that to happen. And because there's not this shared validator set registry for non-Avalanche L1 chains, this is actually a very difficult problem to solve. But we are brainstorming ways that we can approach it using smart contract-based light clients via acceptance proofs, hopefully still leveraging much of this BLS architecture. And then once you know that a block has been accepted, using its state root, you can prove events that have occurred within that block using Merkle proofs. And in this way, we hope to construct a primitive that will work just like ICM as far as sending and verifying messages. So if you've built contracts using ICM, they should be able to work for external chains, but under the hood, there will be different verification occurring. Yeah, so that's this next 6 to 9 months for the interop team. Like I said before, super excited to be here at Summit now that there's a lot of ICM usage. It's super invigorating to see and excited to talk with you all about everything that you're building. I think I'm out of time, but I'm happy to stay after and answer any questions.
Awesome. I think we can give it just one very good question. So if anyone saw this and has a great question, we will have time for exactly one. All right, Ash, on you.
Yeah. So just two quick questions. One is that do we plan to force all the validators to register their bailless keys on the HSM module?
No. So it's definitely not a requirement. Okay. It would be an option for validators to opt into when they're setting up their infrastructure. I think it would be great for node providers to provide that as an option as well for any L1 hosting services like AvaCloud and the like. Okay.
And second is that when using HSM, it adds some latency to the transaction signing. So how do we counter that? Because after async execution, I think we'll be having 200 millisecond block times. So the time difference might add some latency if you're getting signatures from the HSM.
Yeah, so well, I guess two things. First is that the block execution still occurs on the Avalanche Go node side, and that's where the check occurs for has this event been finalized or not. You're just requesting a signature from the HSM after having performed that check on Avalanche Go. The second is that the aggregate signature verification process doesn't happen during block execution. So the only thing this would potentially impact is the end-to-end latency of an ICM message from the time the transaction that sent the message gets finalized to the time that it's delivered on the destination chain and verified there. But the latency isn't significant in terms of needing to request the signatures from so many nodes. If there's a few extra milliseconds while they request the signature from the HSM, it's not really noticeable to the end user.
Awesome. Let's give a great thank you to Michael again.